Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. In this course, we have been discussing an important topic, which is olefin polymerization, and in this context over the last few lectures we were particularly focusing our discussion on polyolefin, particularly polyethylene, and various processes that were prevalent in the beginning for preparing various grades of polyolefin, which can be LDPE, low density polyethylene, or LLDPE, linear low density polyethylene, or HDPE, high density polyethylene. Now, in our discussion we have also looked at several industrial processes starting from that of ICI or radical based polymerizations to produce LDPE to heterogeneous transition metal based chromium centric polymerization method developed by Phillips and properly known as Phillips process for in 1950s 56 to be more precise, for producing HDPE, high density polyethylene. And also how we have looked at how improvisation of the process by replacing the initial high valent chromium trioxide as the precursor with low valent chromosine by union carbide led to accessing these polymers in a more efficient way. We have also seen how union carbide by control the chain length by varying the introduction of hydrogen gas in the polymerization chamber and thereby carrying out a modification of the Phillips process for producing HDPE, and successfully use this Phillips process to produce LLDPE or linear low density polyethylene. In this context, we have also noted the contribution of union carbide in a process called unipole process, where they did away with conventional reactor and used fluid based reactor for producing both LLDPE and high density polyethylene. Now, in and around at this time we have also discussed about the development of Ziegler-Natta catalysis or the origin of Ziegler-Natta catalysis, and what we have noted that Ziegler-Natta catalysis started from investigation on a aluminum based catalysis that would produce long chain compounds of chain length of up to C200 and which was commonly called as the Aufbau reaction. And the Aufbau reaction, in short, is given by (100 bar pressure) produced and then there is this competing reaction called dehydroalumination that resulted in aluminum hydride compound plus alpha olefin. Now, it is while observing the production of long long chain aliphatic compounds that Ziegler observed an opposite trend, and the opposite trend was that that instead of obtaining polymers, what was obtained was 2 molecules of ethylene gave away to one butene. Butane in quantitative yields. And this was a very chance discovery, which sort of showed that something opposite to what was expected. What was expected was long chain polymers, long chain linear long chain aliphatic compounds. This was what was expected from this reaction, but what was found was 1 butene, which is just a dimer of ethylene, and this is sort of a dimerization process, and that was sort of a chance discovery, which was later attributed to nickel impurities. In the reaction vessel. And this in short is called nickel effect. And this was in short called the nickel effect. Now, this nickel effect is what later on was the origin or source of the source for the discovery of this famous Ziegler-Natta catalyst. So, in search of other transition metal that would give premature termination of Aufbau reaction This is exactly similar to what was effect of nickel effect. Another unexpected observation was made. This is kind of very interesting, because if you look, so it is sort of like two serendipities led to one big Nobel Prize award winning discovery. The first one itself was the nickel effect, because people were studying Aufbau reaction, reaction, and was trying to figure out ways and means to increase and make linear long chain polymers. However, they came across this nickel effect, which led to just the dimer. Now, once the nickel effect was found, they were looking for other transition metal that would behave similar to that of nickel effect, and they were looking for other transition metal that would have similar effect like nickel effect on the off-bow reaction, and which would also give dimerized or oligomerized product. However, the other expected observation was that during this search for other metal, they found another metal which could even give much larger polyethylene polymer chains. So, which was again like going back to what they had really wanted in the first place. So, the way we say that 2 left brings us back to the same position. Similarly, 2 errors in the process of discovery led to exactly the same thing what they had wanted in the initial stages, that wanted to make long chain polymers, and that was indeed the case, but that has to be found by first the nickel effect and then another unexpected observation that was made, which led to the Ziegler-Natta polymerization. So, let us see this unexpected polymer. So, it was found that TiCl4 and Et2AlCl gave HDPE, high density polyethylene, at low pressure. Of 1 bar. So, this is indeed a significant discovery, because now unlike in radical polymerization, one could where very extremely high pressures are needed, pressure of around 2000 psi were needed to produce polymers which are not really very long in chain like LDPE. This TiCl4 triethyl diethyl aluminum chloride efficiently gave HDPE, high density polyethylene, at a very low pressure of 1 bar. So, this was indeed a radical discovery at that point of time, because now we have a catalyst which is a titanium based catalyst that can polymerize ethylene to give long chain linear polyethylene at very low pressure of 1 bar, and these are highly crystalline materials without much branching. So, that is the uniqueness about this Ziegler-Natta polyethylene discovery, and this is how it came into being. First, the observation of nickel effect by looking at by getting 1-butene from off-bow reaction, and then the second thing was they wanted to see what other transition metal can give similar premature termination of off-bow reaction, but instead they ended up finding a transition metal which could give extremely long chain polyethylene than even what the off-bow reaction can give. So, with this, let me just give the reaction. HDPE Dalton. So, this is about 10,000 to 1 lakh Dalton molecular weight. So, and these HDPE obtained were almost linear chains with no branching. So, this was very important discovery at that point, which was made by Ziegler, that now he has found a system which is titanium tetrachloride with diethyl aluminum chloride at very ambient condition 25 degree centigrade and 1 bar pressure, and could produce high density polyethylene of very high molecular weight ranging from 10,000 to 100,000 Dalton, and that produced linear polymer chains with no branching. So, this was indeed a great discovery by Ziegler, and what he found that actually the catalyst is beta surface alkylated beta TiCl3, which is obtained from this. So, the real catalytic species is beta form of TiCl3, which is surface activated. Surface activated beta TiCl3. Now, this was the catalyst which was produced, which was producing high density polymer. Now, for this and this process was called initially called as Ziegler 1955 discovered this polyethylene. Or HDPE, and this molar mass 10 to the power 4 to 10 to the power 5 Dalton, and this process was that time known as Mulhem. Normal pressure polyethylene process, Mullen normal pressure polyethylene process. So, what Ziegler found that actually this is surface alkylated beta TiCl3 catalyst was carrying out the process, and they were obtained from TiCl4 and diethyl aluminum chloride. And for obtaining the lower molecular weight, hydrogen was added, H2 was added to control the chain length. Polymer chain length. So, this is similar to what we had observed in case of the Philip process as well, where hydrogen was added to control the chain length, and then Philip process was used for making LLDPE. Now, what are the advantages? Advantages of Ziegler-Natta polymerization, let me just highlight. The first thing is that it could produce at very low pressure. This is the number one advantage. Second thing is that the temperature is also at room temperature ambient condition. So, this is the second advantage. Third advantage is it was producing high density polyethylene which is almost linear and without almost no branching. And fourth advantage is the control of polymer chain length by increasing by adding hydrogen in variation. Now, there are also limitations associated with the Ziegler process. Limitation says that being heterogeneous, the of Ziegler process is a large, a broad distribution of molecular weight of broad distribution of molar mass was of polymer molar mass was observed. So that means broad distribution, the chain lengths varied a lot as we have seen from 10 to the 4 to Dalton, and that means that these are multi-site catalysis. So, to overcome this limitation, the efforts were put into develop single site catalysis. To overcome this disadvantage, single site catalyst were developed. And these single site catalyst, this single site catalyst the catalyst would give a narrow distribution of molecular weight, and so they would give pure or like a more narrower and well behaved type of polymer molecular weight. So, this was the story about the first half of the Ziegler-Natta catalysis. Now, as you can see, the Ziegler-Natta catalysis bears the name of two contributors. One is Carl Ziegler and the second is Giulio Natta, and the first half of the story is about the ethylene polymerization, which was developed by identified and first developed by Ziegler. So far we have spoken about the Ziegler portion of the Ziegler-Natta catalysis, and now we are going to move on to the second half of the Ziegler-Natta catalysis, which is about the Natta portion of the Ziegler-Natta catalysis. Now, in terms of chemical point of view, Ziegler-Natta catalysis uses polymerization of ethylene to give polyethylene, which was Ziegler's contribution, and Natta's contribution had been extending Ziegler's contribution to polypropylene. So, in that way one can say that the real glory about of the discovery of the polymerization actually lies with Ziegler, because Ziegler is the one who had first observed the polymerization of ethylene to HDPE under ambient condition and 1 bar for ethylene. So, extending the same method to propylene would be a obvious extension of the existing knowledge, but the way things panned out is Professor Natta came and worked in the lab of Professor Ziegler in one of the summer, and he understood the implication of propylene that might have in the same catalysis, and so he went and extended the polymerization reaction to propylene, and he very well knew that propylene having a methyl group with have a stereoregular properties in the polymer, and that is he developed that aspect. Polyethylene on the other hand does not have any stereo stereoisomerism issues or stereoregularity issues, because it is just a ethylene backbone, whereas propylene polypropylene had this stereoregularity of the methyl group, and that is another dimension to the polymer that Professor Nata conceived, and that he applied successfully in extending the Ziegler's discovery to propylene substrates. So, today with that we come to the conclusion of this lecture, in which we have looked into the historical perspective of the development of Ziegler-Natta contribution catalysis, right from the time of the Philip process, where the industrial processes were being developed for producing various kinds of polyethylene from LDPE, LLDPE or HDPE. And then how we had also noted that how the discovery of how the study of off-bow reaction to produce long chain polymers led to the observation of simple quantitative dimerization of ethylene, and that was later accounted for the presence of impurity of nickel in the reactor, and that is what was called nickel effect. Subsequent study of the nickel effect for finding another or other transition metal, which would give now the premature termination of off-bow reaction to give 1-butene, however led to an opposing trend or opposing discovery, that in presence of early transition metal like titanium tetrachloride and diethyl aluminum chloride, extremely linear long chain high density polyethylenes were obtained at room temperature and 1 bar pressure. So, this was a great discovery again, which was unexpected, and that is what led to polyethylene polymerization. So, this is the story which was developed by Professor Carl Ziegler, and the limitation about the advantage of the Ziegler-Natta polymerization or Ziegler polymerization is that this produces HDPE high density polyethylene at room temperature 1 bar pressure, and also the chain length can be controlled by metered addition of hydrogen, and the limitation what it had is that it has large distribution of polymer molar mass, the huge distribution of the molecular weight, and that suggested that this is a multi-site catalysis, and hence to improve on that the focus changed to synthesizing single site catalyst for making more well behaved polymer with narrow polydispersity index. So, with this we come to end of the Ziegler story of the Ziegler-Natta polymerization, and we are going to be taking up Natta's story the next as a part of the Ziegler-Natta polymerization, and how we would see how Professor Julia Natta translated the knowledge developed by Professor Ziegler for polymerizing polyethylene, and use the same on propylene to produce polypropylene, and how that was developed in subsequent ways. So, with that I again thank you for being with me in this class, and we are going to be discussing more about this exciting story of Ziegler-Natta catalysis as we meet next in the next lecture. Till then, goodbye and thank you.